Courts of India. This is again an interesting news article which says that in Bihar's Bhojpur district, a case was resolved after 108 years it was pending. And I think so there's a general consensus that tech needs to come to the aid of justice delivery. So let's not try to break down our thesis title to understand what exactly we are here to achieve. So enabling legal artificial intelligence via bail prediction on Hindi case documents. So let's break down each of these terms. So legal artificial intelligence or legal AI is concerned with the use of AI technologies, particularly NLP to legal tasks. We focus in particular on NLP because the resources are generally case documents, constitution, i.e. the written text. A bail prediction. So bail is a decision whether a person would be granted or not, and it's the interim release of a person suspected of a crime. So here our objective is to build a bail prediction system out of it. And thirdly is the Hindi case document. So our focus is specifically on Hindi documents only. So what's the motivation behind it? Judiciary is one of the 3 pillars of democracy, and it's critical to the functioning of a nation. However, in recent times, courts have become inundated with a large number of pending cases, which has slowed down the judicial processes. Hence, there is an imminent need to have systems which can process these legal documents faster and help in the aid of judiciary. So this is a very blanket statement that we made here. Courts are inundated with a large number of pending cases. What we need to understand is exactly where are these cases pending. So according to India's NJDG data, there are 40 million cases, which is approximately 4 crore cases pending in the district courts of India, as opposed to only 5 million cases pending in the high courts. What this highlights is that there is a need to address the problem at the grassroots levels, targeting the district courts of India. So this is just to provide a brief background. The judicial structure of India is a 3-tiered system. The lowermost rung composes of the district courts, where the majority of the cases are handled. And these are eventually trickled down to the high courts and Supreme Courts based on whether the decision is contested in the lower courts. So what are the challenges in building any system which tries to address this problem of the district court? So the challenges are twofold. First is language. So the case documents in the district court uses the local language of the state, as opposed to the High Court or the Supreme Court, where they consistently use English. So this is just an article of the Constitution of India, which states that all proceedings in the Supreme Court and every High Court shall be in English language. However, we see there is no such law for the district courts. Hence, there is abundant use of the Hindi language here, or the local language of the state. And structure. So each district has their own convention. These are all independent bodies per se. So there is no really quality check, or there's no consistency across the districts. And additionally, these documents are highly unstructured in nature, with rampant spelling and grammar mistakes that we need to correct in any system that we build. So to set some background to understand what all work has been done in this legal AI sphere, we look at some prominent legal corpuses. So one of this is Chalkadis et al., which is an English corpus of European Court of Justice documents. So we categorize this as a non-Indian context English document corpus. There are works which are in non-English, other languages other than English as well. So we have Zhao et al., which was a Chinese legal document corpus. So again, this is a non-Indian context, and this is Chinese and family of Chinese language, basically. And then we had Malik et al., who developed it in the Indian corpus, in the Indian context, using the Indian Supreme Court data. But here we see, while we have the Indian context, it is a Supreme Court and thus English language. So we see a huge gap here where there does not exist any legal document corpus for the Hindi language. So that comes to our first contribution, which is HLDC, Hindi Legal Document Corpus. About 40 million cases, pending cases in the district courts of India were identified. And we looked at the distribution of these pending cases and saw that about 20 million of them were in those states where Hindi was the official language. So this is why we started to focus particularly on Hindi. No legal corpora exists for Hindi. And hence we proposed HLDC, which is a corpus of over 900,000 Indian legal case documents. And it was created by crawling data from the eCourts website, which is a Government of India initiative to track and analyze case progress online. So let us look at the corpus creation pipeline. So we see that we have initially the eCourts website through which we extract the data out. Once this raw PDF documents are out, we apply OCR on top of it to get the text documents out. So this would give you an example of what is the sort of PDF document that we're able to achieve. There are certain nuances to notice here. We see that there is presence of both English and Hindi characters here. Thus, our OCR needs to be able to handle both of them well. Once OCR was done, we need to chunk this or segment this large blob of document into its parts. So what we did is we did a coarse granulation into the header and body. So if you look at this, the majority of initial stuff is initially metadata like when was the case, what's the case ID, date, who are the petitioner and defendant, what are the dhara, or basically what is the IPC section under which this case is filed, location, thana, district. So all these were the metadata which was associated and comes under the header body. And the header and the rest comes under the main body of the. Once this is segmented into the header and body, we had this final cleaning process, and which led to the creation of our HLDC corpus. Now, once this corpus is created, this serves as a source for multiple NLP application and tasks. So one is like a prior case retrieval. So given a particular case, we want to identify if a similar case exists in the past or something of the sorts. The second is legal summarization. So if you have a larger case document, you want to provide a summarized version of it. And what we show here is a bail judgment prediction. So as a utility of the NLP corpus, the HLDC corpus, we show the bail judgment prediction. So coming to some of the challenges that we mentioned earlier, there were other processing and cleaning steps that needed to be done on this data. The first was the anonymization challenge. So the purpose of the anonymization was twofold. First, we wanted to create unbiased models. So any models that we create later using this data, we didn't want the information like what's the person's name, location to trickle into it. We wanted any decision just to be based on the actual facts of the case. And the second is privacy concerns. Certain cases are very sensitive in nature, and it's important to understand that we don't want to harm the sentiments of anyone by releasing it public. So what we ensured is we had NER procedures to ensure that the data was anonymized. So if you look at this particular case document, you can see that person's name is available. So in our final release corpus, these names were identified and replaced with a common NAM tag. Similarly, there were instances where the phone number was made public in the legal document, which were identified using the regex expressions. And those are also removed and removed with a single label phone number. The second is, if you look at this particular slide, this is an actual screenshot of the eCourts document. And you can see that each case document has an associated case type to it. So it basically tells us what that particular document is. And if you notice here, what we see is that there are repetition and there's lack of cleaning in the data. So if you see that bail application, once it's written in camel case, the other time it's all caps locks, there are other spelling errors across the board. So this was the standardization challenge. There are different case types. And what we wanted to do is that we wanted to create a uniformity across these case types. So as you can see, bail applications were categorized as bail APPL or bail application in Kanpur Nagar district. There were other variations based on spellings and all. So all of these were fixed using edit-based distance and manual verification. So we get a nicely curated list. So these are the case type statistics for the HLDC corpus that we observe, and we see that the majority of cases, more than 30%, are composed of bail applications. So now we have, at this point, we have completed the first contribution, which is our creation of an HLDC corpus, which can serve as the base source to build different applications on top of it. Now, the natural question arises is what is a relevant application to build? And what we did is we went ahead with bail prediction tasks. The reason for this is as follows. We wanted to showcase the utility of the HLDC corpus, and the most prevalent case type that we observed was the bail prediction. Additionally, bail cases are very time sensitive in nature. because these have to be processed immediately, otherwise the defendant or the person accused would remain in prison essentially. So these needs to be immediately processed. Hence the time period to resolve this is like 7 to 15 days as opposed to other cases which might take years to resolve. So keeping this twofold factor, that being very time sensitive in nature, and second, these are the most prevalent case state, we went ahead with the bail prediction task. So just to capture what the bail prediction task essentially is, you have the facts and arguments of the case as the input. You have to build a system, which is the bail prediction model, which will give you a binary output whether the bail is granted or denied. So this is in concise what our system is all about. So now the HLDC corpus has to be modified for this bail prediction task. So what we did is, using the case type identifier that we had, we filtered out bail documents from the HLDC corpus. After this bail documents were filtered out, we went to the outcome identification. We need to know whether what is the true label to a particular bail document, whether the bail has been granted or denied. And we also did opinion mining, judge's opinion mining, where we extracted the judge's opinion out of the bail documents. I'll go into it a bit later. So what is outcome identification? It's just a binary label, which is to identify if the bail is granted or denied. And to extract this bail decision out, we manually identified certain keywords which are present in the result section of the document. So which were keywords like kharij, dismissed, nirast, invalidated, or cancelled shows that the bail application has been denied. While similarly, words like swikar, accepted, that shows the identification or acceptance of bail application. This is an actual bail application which was denied, and you can see nirast kiya jata hai, which is basically invalidated or dismissed. So these are a list of tokens that we identified, which were these. It's a non-exhaustive list. There are more in the paper, but this kind of gives you what are exactly the tokens, manual keywords that we looked at. So is being accepted by accepting accepted. These are the Hindi words and their English corresponding translation. Bas nirast kiya jata hai, nirast kiya jata hai, and different forms of it. So this was in the outcome identification part. Then we come to the second part, which is the judge's opinion and facts extraction. So as I said earlier, what we observed in the bail documents was most of them had a concluding paragraph where the judges kind of summarizes their own take or the entire facts and viewpoints of the case. So what we did is, again, to extract this, we based on annual observation, we constructed certain regex pattern, which often precedes any judge's summary. And finally, after extraction of the header, which was done earlier, the facts of the header, the outcome identification, and the judge's summary, whatever is left is essentially your facts and the bulk of the case. So again, this looks at some of the tokens which were used for the judge's summary extraction. Here we see hearing the arguments of the parties, perusal of the records as per the evidence available. So all these precedes the beginning of your judge's summary. So now we have come to a state where we can formally try to define what our exact problem statement is. We are given a set of bail documents, so BI to BK, some set of bail documents, and each bail document here has been further segmented into the header, the facts of the cases, the judge's argument, and the final outcome, which is the YI identification. So here HI, FI, JI, and YI represent the header, facts, judge's summary, and the bail decision of the document respectively. And each sentence, a fact or the main facts of the cases are composed from multiple sentences. So you have like SI to SK, whereas it represents the ith sentence of the particular fact. So what exactly are we looking here to model? What we are looking here to achieve is we are trying to find the probability of the outcome YI given the facts of the case FI. So a very important, interesting thing to note here is we just use the FI and not the GI to make the decision. What it basically means is only the facts of the cases are made in the final prediction model, not the judge's summary, because that's something that will only be available on the input of a judge. So as a system, our bail prediction model should be able to take just the facts of the case and give you an output, which is your probability decision YI. And it's 0 if bail is denied and 1 if bail is granted. So now we have the problem statement formulated, and now we are in the state where we want to build models to essentially solve this bail prediction task. So we naturally progressed from the embedding based models, which are the simpler models, going through summarization based models, and finally coming to a multitask learning model. So this is gradual progression based on what our observations were. So first we started with embedding based models. So this was again simplistic methods like talk to it, classic embedding based models. And once we got these embeddings out, these were trained on SCM and XGBoost classifiers. And this is just a classic embedding. So we also wanted to try out transformer LM based embeddings. So we used IndicBERT, which is a transformer language model trained on 12 major Indian languages. But there are certain constraints which comes as soon as you use transformer-based models. One is the limitation on the input length. So it has like maximum 512 tokens. So what we did is we experimented in two different settings. In first case, for the entire facts of the cases that we had, we took out just the first 512 tokens and fed it into the model. And in the second case, we had like the last 512 tokens of the document and fed it into the model. So basically so what exactly are we doing here? What we are seeing here is that we are taking some segment of the document out, which we feel is important. So maybe the information is captured in the first 512 tokens, things like whether this case is serious or not, or what exactly is the crime and XYZ. So the fact here is we are arbitrarily selecting first 512 and last 512, where our goal should have been to select the smart 512. What basically it means is, can we identify where the input signals are actually in the main document and keep those tokens only? So this is what the problem boils down into. We have a lengthy document and we want to perform summarization on it to keep the important things available to us. So this has a twofold benefit. First is that, of course, extractive summarization of the document will reduce the length, and thus our transformer LM-based models will work on it. The second is summarization is also building up towards some sort of explainable AI systems, which is we are able to kind of understand that which are the sentences that a model is actually thinking is important, or what are the things that it feels will help us to make a decision. So now we go into the summarization methods. So we had the unsupervised approach where we did not have any need for any ground truth or silver truth summaries. So this was a basic TF-IDF model, which is just taking the term frequency, document frequency, and identifying the relevant sentences and just passing it to an IndicBERT model. We also had a text rank model plus IndicBERT, where we used the graph-based method text rank, which is based on the page rank model, and based on the sentences it was selected, we then passed it to the IndicBERT model. So these were the two summarization approaches. And then we also had an interesting semi-supervised approach. So what we did is we used the judge's summary that we had as a truth indicator to train an additional saliency classifier model, or basically a summarization model, to tell which are the important sentences or salient sentences. So I'll dive into this now. So this is a semi-supervised summarization approach, which is our saliency classifier. So what we had is, what a saliency classifier is, it's a binary level classifier which says that whether a particular sentence is important or not. So it's just giving us a 0-1 label. What we did is we had a multilingual sentence encoder to compute the embeddings of all the sentences in our facts. And we took the summarized judgment as our silver standard, saying that if your facts are similar to this, what the judge is kind of saying, that's an indicator that your sentence is relevant, it's salient. And then we use basic percent similarity score to measure how similar or how good a particular sentence in the facts is. And based on it, we had a ranked list of sentences for our facts. And we said that the top 50% are salient and the bottom half is non-salient. And we used this data to basically train our saliency classifier. Another fact to reiterate that whenever we are evaluating a system, we'll not use the judge's summary to evaluate our model. That is independent, that's not used in our final prediction model. It's just the facts of the statement. And again, the salient classifier are used to train the IndicBERT-based classifier that we have. So I'll just point out here to the results. So what we see, the last three rows are the ones which have a factor of summarization to it. And we see that they outperform the ones which are more similar embedding-based models or without summarization models. This tells that summarization shows an improvement in results. So now what we had done earlier is we first do a summarization and then followed by a prediction. What we did is a multitask framework so that do both the summarization and the prediction task together. Hence, the bail prediction was our main task and the sentence saliency classification as our auxiliary task. So this is our model architecture. We had a Bail documents. It has a large number of sentences S1 to Sk, which are encoded using a multilingual sentence encoder, and thus we had our contextual sentence embeddings out. As you can see that these are just frozen parameters. These are not updated during training time. What we did is we appended a randomly initialized CLS token to it and simplified it to a single transformer layer. And finally, we had our heads as fully connected MLP layers. So we had a bail predictor head and a saliency classifier head, which is just MLP, fully connected MLP layers. And then this is used to compute the final loss. So final loss is computed for bail as L bail, which is represented as bail, is just the binary cross entropy loss, and standardized cross entropy loss for the saliency classifier. And the final loss was taken as an equal weight of both the bail prediction loss and the saliency classifier loss. So our final loss L total is just L bail plus L saliency. So this is our architecture model that we had. And we experimented it in two settings. First was an all district performance. What we did is we had a 70-10-20 distribution of the train, validation, and test split. And documents from all the districts were pooled together to do this split. And in the second, which is like the district-wise setting, what we did is we had documents from 44 districts as part of a training corpus, documents from 17 districts as part of a test corpus, and 10 districts as part of a validation corpus. What here we want to test out is how well our model kind of generalizes, saying that if you just see data from some other district, can you still predict actual bail documents from some other district, which was not in the training set. So this is just the distribution that we have, and it's an almost 60-40 ratio of bail granted to bail dismissed documents in the entire corpus. And this is just the distribution that we have for all district and district-wise distribution. And these are the results that we have. So we do observe that our multitask learning approach performs the best in the district-wise data setting. And additionally, even in the all district setting, it was pretty similar to any other approach that was tried out. So first thing is that for all the cases, we see that the district-wise settings, the performance is relatively lower than the all district setting. It's because it's tough to generalize across districts. However, our multitask learning approach seems to be capturing robust features, which seems to generalize well. In the all district setting, it's probably lacking or like coming short compared to even similar TF-IDF based summarization models. It could be down to it's probably down to the fact that we are still using cosine similarity, which is a heuristic metric to identify which sentences to keep. So there are bound to be errors in that. So this is a very interesting plot which looks at what exactly is the distribution of our output. So what we see is that while our final model is giving this binary label, which is bail granted or bail denied, the actual model output is going to give us a gradient of values, which is based from 0 to 1. So what we are plotting is basically what is the output of our model prior to the final 0 and 1 labeling. So this is very interesting to note, because in a real world application, if you want to apply it out, you don't want a scenario where you give the judge or you give the end user the output that it's only 0 or 1. You want to give them a probability out, because then you have a confidence associated with it. So basically what this graph shows is that those which are correctly dismissed, that means our model predicted it as dismissed and it was actually dismissed, those are all leaning towards 0. So basically our model is able to say that, okay, your score should be very low, and they were actually also very low. Similarly, those which are correctly granted, which is this blue label, which is leaning extremely towards 1, which says that a model was giving it a very high score and it was actually granted. And the ones which are actually incorrect by our model, these are somewhere around the 0.5 marks. So suppose you get a bail document out and your model is giving it an output of 0.49. What it does is your model will say that it's bail denied because it's closer to 0. But actually this information, it's giving you far greater information. It's giving you information that it's very close. It's a borderline case. A very simple, what it basically means is that we could have a system which could be like 95% accurate if we keep the thresholds accordingly. We can say that anything which is less than 0.2 is classified as 1, greater than 0.8 is classified as other, And in the range of values, I am not sure. That's what the model is kind of telling us. So this shows that there is utility here. There's utility here where we can provide this confidence score, and those which are very confident on streams could be automated to some extent. So now let's look at the challenges and limitations to what exactly we have tried to explore. First is the domain-specific knowledge. Basically, these code documents have very specific lexicon. So any pre-trained model which is built on other corpus doesn't perform as well. Second is under-resourced or low-resource language. So this Hindi, despite being the third most spoken language in the world, remains an under-resourced language in the context of NLP with limited high-quality training data and pre-trained models. And a couple of these challenges go hand in hand. So if you look at the length of documents, that was another constraint that has, because court cases are very large documents, and thus simple transformer-based models have this constraint of 512 tokens, which we're like trying to overcome. So it makes challenging to process legal documents. Now, what I wanted to say is that some of these challenges work in conjunction. There are ways to overcome the 512 tokens by long-form-based, transformer-based models, but then those are not very readily available for the Hindi language. So thus we see that, and then you have the constraint of domain-specific coming into play as well. So all these challenges kind of go hand in hand. So just summarizing all that we have done till now. So we introduced a large corpus of legal documents for the under-resourced language Hindi, which is HLDC corpus. As a use case for HLDC, we introduced the task of bail prediction, a time-sensitive and impactful problem to tackle. And we experimented with several models and proposed a multitask learning approach that predicts salient features as an auxiliary task and bail prediction as the primary task. So what next? Where this kind of work can go into, where it can build upon. First is multiple languages. So India has 22 official languages, but for the majority of language, there is no legal corpora. The use of such corpora, so another factor is that the use of such corpora is not only restricted to a particular task in legal NLP, it can also act as a source of unsupervised data, because the legal documents are really large bodies of work. So you have hundreds of documents which are very large in nature. So if you want to build train some transform models from scratch for a particular language, this data could be used. Second is infusing domain-specific knowledge. So what we want to do is, as we said, that legal has their own specific lexicon. So there are works in legal word, but again, that is again for the English language, not necessarily for Hindi language. But trying to train the models from scratch, have it infused with knowledges from sections of ADACs in the IPC section, Constitution of India, other legal things, to capture these legal nuances, basically. And the third is a very obvious other legal NLP task. So we have our HLDC corpus created out, and this could be used as a source for things like legal summarization and dry-based retrieval. So the majority of this work was part of work which was published at this year as a long paper in Findings of ACL 2022, which was a collaborative effort between work from IIIT Delhi, IIT Kanpur, and IIIT Hyderabad. So that's all. I would like to thank Professor BK for his constant support throughout this thesis journey, Professor Saptarshi Ghosh and Professor Srijani Sen for taking time out of the schedule for this and giving insights about the thesis. I would also like to thank Professor Ashutosh Modi and Professor Arna Bhattacharya, who were collaborators in the previous HLDC paper that I showed. Thanks for the opportunity for working on such an impactful problem. I'd also like to thank IHUB for funding my master's, to all my friends and the pre-co group here for their constant support and encouragement. And thanks to my family for everything. My mom, my dad, my sister. Yeah, that's all. So questions?